This lecture is a bit of the basics of decision theory, how to use statistics in the making of decisions. And so let's lay down some background, tell you a few of the facts of life. Some decisions have to be made when the facts are not absolutely clear-cut. At times like these, you know certain data and certain actions will have to result from it. Okay, and in cases like this, it's helpful if you can have some criteria set out to aid the decision-making process. Okay, so let's take as a model the jury trial. Okay, in a jury trial, we have a person accused of a crime, and okay, the person is presumed to be innocent. The prosecutor must argue that he is guilty. The jury must weigh the facts that are presented and decide. Okay, so here, this is the world, and along here, these two things, they represent the truth. Either the accused is guilty or the accused is innocent. And here we have the decision to be made. Okay, the accused is found to be innocent, found guilty, or he is found not guilty. Okay, now if he is innocent and he is found guilty, that's an error, right? If he is guilty and he's found guilty, okay, the correct decision was made. If he's innocent and is found to be not guilty, that is the correct decision. And if he is guilty and found not guilty, that's an error. Okay. Commentary. In our justice system, it is considered to be worse to put an innocent person in prison than it is to let a guilty person go free. We therefore let the jury set the standard that jurors must be sure beyond a reasonable doubt. Okay, so we take a statistical model and distill it from these principles. Okay, a statement is considered whose truth can be tested. The statement is assumed true for the sake of argument, and it's called the null hypothesis, and we denote it by an H sub 0. Frequently, I'll just say H naught. Okay. The logical negation of the null hypothesis is called the alternate hypothesis, and we will denote it HA. Okay. So a level of reasonable doubt is set. A method of arriving at a decision is determined. Okay, and after all of these pieces in place, then data is taken. Okay, if we have the procedure set in place before we take data, then it's safer to assume that our procedures haven't been skewed by the information we obtain from the data. Okay. The data is then processed and a decision is arrived at. If we decide that the null hypothesis is not true, we say that we reject the null hypothesis. Okay. So again, we have the world of true and false. Either H is true or H is false. Okay, we need to deal only in statements like this. And in terms of our actions, we either say H naught is rejected or H naught is not rejected. If H naught is true and it's rejected, this is an error. and we call it a type 1 error. If H naught is rejected and it's false, well, that was the correct decision. If H naught is true but it's not rejected, well, that's the correct decision. If H naught is false but we don't reject it, that's called a type 2 error. Okay. In the statistical model, a type 1 error is what happens when we decide to reject a correct null hypothesis. It's sort of like, okay, you're in a boat, okay, and it's sinking, but it's not really sinking. That's a type 1 error, okay. You want to stay, the idea you want to stay in the boat, right? A type 2 error is, okay, it really is sinking, but you decide to stay in it, okay. Significance is the probability that we have a type 1 error, okay. And this is the one we try to control it. We try to control the type 1 error. Okay. So, practical terms. We will be dealing with the hypothesis test of the mean. A null hypothesis for it is going to be of the form that mu is equal to some mu naught. This mu naught is going to be a literal number. This mu is always going to be a variable. It's always going to represent the mean. But this mu naught is some actual literal number, like 14 or 73, something that is actually written down that you can measure, and it's not, we're not going to have a variable there. Okay. Now, we have our null hypothesis. We're assuming that mu is true, but when we take data, as we see, even if mu is true, the x bars can land all over the place. Okay, so we set a margin of error. Okay, all right, beyond our mean, and what we're going to say is, okay, if we draw a sample that's farther away than this, we're going to say, oops, we're going to have to reject our margin of error. We're going to, reject our null hypothesis, right? Because we're saying, even though it could be true, it's only a small probability that it could be true. The sample mean falls in this shaded area the shaded area has total probability alpha. Exactly when this mathematical condition holds, okay, that when x bar minus mu naught over sigma divided by the square root of n in absolute values is greater than z sub alpha over 2. This z sub alpha over 2 is called a critical number. Okay, so when our test statistic is bigger than our critical number, we'll say, oops, this is just too far off for me to pretend that I believe this anymore. Okay. Case study. Johnny come lately, the new man in quality control, has been left in charge of the sack filling machine while the manager takes the day off. A disgruntled employee slams the filling machine with a sledgehammer and leaves. The machine is still filling bags, but it may be misfilling them. Stopping the machine to repair it would cost in lost production, parts, and labor. Okay, the sacks are supposed to be filled with 5.025 pounds of sugar. Okay, company policy only allows the line to be shut down unnecessarily with a 5% chance. What should Johnny do? Okay, well, the truth is, if this is a well set up corporation, they've got policies done, and so something like this will be set up, that you have mu you're going to assume that the machine is filling correctly, okay, and you'll have to prove that it's not filling correctly if you want to shut the machine down to fix it. Okay, so this is, we only want to shut it down in error 5% of the time. We divide the alpha by 2 to get, because this is what's called a two-tailed test. You divide the alpha by 2 to get 0.025. And this gets what's called our critical number, right? A table lookup on the Z table. And so we put this there. This is what we call our test criteria. This is saying, okay, all you have to do, oh, do I do this or do I do that? I don't know what to do. I'm so much anxiety. Help me, help me, help me. All you have to do is to take your sample. Let's see, where is that? Yeah, okay. And put the number in here and then do the math. If you get a number that's bigger than 1.960, you stop the machine and fix it. If it's less than this, even if it's close, you let the machine run. Okay, so Johnny takes a sample. You take a size 45. You have to take a sample size bigger than 30 for this to work. And it turned out that X bar was 5.01, and that's maybe a little smaller than the company likes, darn it. Standard deviation is 0.1. Okay, you put the number in here, and okay, it's not greater. Okay, this is not greater than 1.960. We don't reject the null hypothesis, which means, okay, everything's okay. We assumed everything was okay, and we weren't able to prove otherwise, and so the machines won't be shut down. We're not going to lose time. We're not going to lose money. So, and Johnny, come lately, does not lose his job.